Okay. All right. So we're going to go ahead and pick up on example number 6 on our 12, I'm sorry, 2C12 part B notes. Okay. This is talking about vertical dilations being equivalent to a horizontal translation. So we're going to talk about how this comes into play with the change of base property. So we talked about the change of base property. Log base x equals log of a x over log of bx. So log of the argument over log of the base. Okay. A has to be positive. A can't equal 1. So we're going to use to show this is a vertical dilation of the function f of x equals log 2 of x. So if you have f of x equals log base 2 of x, right? That's the original. That's where you're starting, right? I can rewrite this as f of x equals log of x divided by log of, it's supposed to be a big 2, not a little 2. Let me make mine too big. Log of 2, which can be separated. When you have a fraction, I can write this as 1 over log base 2 times log of x. So notice that this, when you write it in terms of change of base, it becomes a vertical stretch or dilation, a vertical dilation of the common log. That's the main purpose here, is to let you know that given any log of any base, it is equivalent to a vertical dilation of common log. That's the whole gist of that piece right there. So what that means, if I go here to my handy dandy calculadora, hey Sylvie, hey girl, hey, I'm going to reset because I've been doing some stuff a while now. So we have y equals. If I hit alpha window and I type in log base 2 of x, and I'm going to hit graph so we can see what the graph looks like. Hit the graph. Okay. Yes. I'm also going to then type in on y2, I'm just going to type in log. So I'm just going to type in log of x, which is our common log. Common log means that your base is 10, correct? So I'm going to type that in and I'm going to show you. So there's common log and there's that log. This right here, that 1 over log 2 times log x, if this is accurate, if it's a vertical dilation of the common log, when I type this, it should replace my blue. So I'm over here. I'm going to put in parentheses because I can't make fractions. You can on yours. I'm going to type 1 divided by the log of 2, close parentheses, times the log of x. I have to use parentheses, double parentheses, because I can't create a fraction. You can create a fraction. No, you can close it. It's flow of air. Huh? Yeah, but my room collects moisture, and so when the door closes, like literally that's hiding mold, that brown paper. So that's why it's always open, in case you were wondering. It was a safety reason for health. Okay. So they're probably like, what is she doing? Why is her room always open? So when we go here and graph, notice that it's graphing, but is there a third graph? It's the same. And that's because any log-based function is just a vertical dilation of a common log. So when you look at the values on the table, see that y1 and y2 are the same. So that's why my blue line became a black line, because they are the same value. And that's the whole premise of that little thing, is explain that this is why that works. Okay. All right. But anyways, it says graph both f of x and g of x. So g of x is a transformation of log. So I'm going to go back. I did part A already, so now we're going to do part B. I no longer need to talk about the common log. Common log gone, common log gone. Now, I'm going to transform this. Looking at log base 2 of x minus 1, in your brain, what should happen to the graph? What transformation is taking place? shift to the right. So we should know, we understand that when I graph this, it should be a shift to the right. Alpha window 5, log base 2, x minus 1. This should create a graph that is vertically shifted, I mean horizontally shifted to the right. So there's my original. And there's my translation to the right. Okay. Yes. All right. I'm not going to graph it. I'm going to move Sylvie right here. There you go. There's my graph. It says describe the change in the output. So from f of x to g of x, what took place? So describing, so from f of x to g of x, what took place? Well, as x values increase, whereas there's any change to the y values. No, there was no change to my x value. As x values increase, however, there was change to my x value. So from f of x to g of x, as x values increase, x values translated. That's why it says to describe your input because there's no change from output. Well, it says output over, but x values translate 1 unit, right? And y values remain the same. And that was poorly written. I apologize. There's a space there. Okay. So now we're at the point where when we're describing transformations, we're not just saying it went left, it went right. We have to say how does it affect our x and our y values? Okay. Uh, and go from there. Is it y values? Yes. Y values remain the same. If it's easier, you can always move up here with Miliana. You need a better later view. Oh. All right. So here we have natural log. So natural log, remember, is just simply log base e of x. So instead of writing log base e, it was transformed into ln of x, natural log of x. That's all natural log is, log base e of x. So when we have here f of x equals -2 natural log of x plus 1, it says find the domain of f, okay? Notice that it doesn't say graph first. It says find the domain. That means we're establishing the domain before we even graph the function, okay? Your domain is based off of your horizontal translations. Does that make sense? Your horizontal translation dictates your domain, and that's because there is a vertical asymptote. So my horizontal translation says that this is moving where? To the left, because I'm horizontally translated to the left. That means that my domain starts at -1 and then it continues to infinity. Does that make sense? Okay, so to show that we're correct, and the reason why I use parentheses is because there's a what? Anyone? There's a vertical asymptote, so that means it won't ever equal. So I'm going to go to y equals. I'm going to clear out what I have, and I'm going to type in. I'm first going to type in the parent function. So I'm going to type in ln of x. No, ln is right on the key. And I'm going to type in -2 ln of x plus 1. So when I hit graph, the one on our paper, -2 natural log of x plus 1. So parent function is blue. Were we correct? Did it shift to the left? Yes. So now our domain starts at -1. Okay. All right. So when we graph it, we graphed it. Let me keep up the graph because again, so we don't have to judge Miss Jones and her artistic abilities. We're just gonna let Sylvie be great right there. Okay. Um, Usually lets me see like it bigger. This no. Okay. I think I did something. I think I angered Sylvie. Oh no. She's glitching. Sylvie, ignore. You're great just the way you are. All right, state the range in asymptotes. So the range here, because log is the inverse of exponential, our range is going to be all real numbers, right? So our range is from negative infinity to positive infinity. And we have a vertical asymptote at x equals -1 now, right? That's where that imaginary line. Now it says state any intercept. So you're looking for where do I cross the x and y axis? You have a couple options. You can first start with the table and see if it's clear for you to state where your x and y axes are, your x-intercepts. When you're moving through the table to go up, you just got to use, up and down. So I can see that I have at 0, 0. If I'm at 0, 0, then that's my x and my y, right? So we're at 0, 0 on our transformation. You can also go back to the graph, and if you need to zoom in, you also can see that it crosses at 0, 0. Okay, now we're going to describe function behavior and concavity. So your do now today should have had you start thinking about concavity again, right? And get you in the minds, okay, how can I describe this? Function behavior is saying as the function is growing from left to right, or as it's approaching your asymptote, what is it doing? So how can I write this in a sentence, like a numerical sentence? Everybody scream. We take attendance. Who's absent, guys? Even Chelsea. I love that when you're trying to teach and you have the brain farts and like, oh, I didn't do something. It's a little tacky. This just means that me teaching y'all is way more important. That's all that means, right? All right, anyone, sentence. It's concaved up. Good job. So we can write it as first, we can describe the fact that it's concaved up is because it's a decreasing function, right? So the function behavior is decreasing. Agree? And it's continuous. There's no gaps or hole. And it's concaved up, as Emiliano told us. Okay? We're going to just write our limit. Because there's an asymptote, remember when we write our limit, we are approaching that asymptote, right? We can't say it's going forever to negative infinity. We're going to acknowledge the fact that there is a asymptote. So because there's an asymptote, our limit as x goes to -1 from the right, f of x is heading towards what? Positive infinity, right? F of x is heading towards positive infinity. And our right-hand limit is as the limit as x goes to positive infinity, f of x is heading towards what? The red is going where? Negative infinity. Question? Or stretching? Oh, stretching. Okay. Does any of those words or format make you have questions or confusions, point of confusion?
Why is there a negative and a positive with the x goes to 1?
So this means, remember, if I write this little plus sign, that means I'm coming from the right towards that boundary. If it was a negative, I'll be coming from the left towards that boundary. Okay. Huh? Well, if you have, when you have an asymptote, you have to be describing, are you approaching it from the left or are you approaching it from the right to describe what the function is doing? Because when you get to rational functions, they could be doing this, right? So coming from the left, it could be going towards negative infinity, and coming from the right, it could be going towards positive infinity. So that's why we use that little plus and minus to say, which way are we looking at the asymptote? Okay. And this way, we only can approach it from the right, right? Coming from the left is nothing. Okay. Questions? Do y'all need me to draw the picture? Am I okay if I'm being lazy?
Okay.
Nice try though, Max. You're the only one that said it. So we're going to keep it going. Uh-oh, I went the wrong way. I went the wrong way. All right, last example, right? So our last example, we have natural log of x minus 3 squared for x is less than 3. Okay. Notice here that this is 3 minus x. That 3 minus x lets us know that our uh our x is negative. And because our x is negative, that's going to be what type of transformation? A reflection over what? The y-axis. So we're going to have a reflection over the y-axis. So instead of us seeing our traditional log going doom or doom, it's now going to be heading towards the asymptote. So this will be an example of us approaching it from the left. Does that make sense? So we're going to be approaching our asymptote from the left. All right. So when I look at this, it says find the domain. Your domain again depends on what are your x's doing, how your x is behaving. Okay. And it says for x is greater than less than 3. So we're only looking at it from the left side. Does that make sense? So we're only looking at from the left side of 3 what is happening, because it says for the values that are less than 3. Okay. So there is an asymptote there. There is an asymptote because this is my key that there's an asymptote, right? So we're going to rewrite this in a different format. So written correctly, this would be written as, well, mathematically, natural log of negative x minus 3. And that's why your asymptote is at positive 3.
Okay, I understand that.
Okay? Oh, I forgot the square. Thank you. The square just means that this whole function is squared, but this is what you're reading on the inside. So that means it's duplicated. It would be, I'm going to graph so you can see it. Okay. But this means that's why it's reflected, and this is why you went to the right and not to the left. Does that make sense? Okay. See it? Yeah. So find the domain. Well, it told us that we're only going up to 3, right? So we're only going up to 3. And now that I see that this negative in front lets me know that there's a reflection over the y-axis. Instead of 3 being my starting point, 3 is now my ending. Does that make sense? So my domain starts at negative infinity and it works its way up to 3. And now we're going to graph to confirm whether okay, so I'm going to go here. I'm going to go ahead and take that out. And I'm going to type in natural log of 3 minus x squared. That's not a square, is it? Yeah, it is. Okay, so it's coming in slow and not hot. And then it did what? That square made it duplicate itself. Okay, however, are we paying attention to the right side? No, because what did it tell us to do? X is less than 3. So we're only paying attention to the left. That's the only piece that we would graph. Does that make sense? I'm actually going to graph this one, but I want you to see what the square does to it. Okay, so I have my asymptote and I'm going to graph my points. So my key points that I'm graphing are 2, 0 and 0, 2. It looked like that's where it hit. And then I'm going to do my best to just sketch it out. It's me concentrating, guys. Yep. We're gonna pretend that I touched that. Oh yeah. So here's my vertical asymptote at x equals 3. Here is my reflected and stretched by a factor. Why? Oh, I did go too far. I had it's going. It just doesn't show it. So like it looks like it stopped, but that's because um the values are approaching 3. So they're gonna get closer and closer, but they're going and going and going and going. It's just not gonna show that graphically. So both sides are going, they're approaching it. It's an asymptote. So it can't stop before that asymptote lets you know that it's going forever down, which is why I said let me draw it for you. Does that make sense? Like you don't see it, but it's going, which is why I wanted to draw this one. Okay. Now, the reason why this works like this is because, um, yeah, the square. The square is the whole reason. That square is also acting as a stretch because remember the log property rule, the power can also be your coefficient, correct? So the power can be your coefficient, which is why it's stretched. So this graph, looking at this transformation, it is a vertical dilation, and that's because of this little 2 here. So it's a vertical dilation by 2. It would be reflected over the y-axis, and it was translated 3 units right if it was compared to its parent function. All right, your range. So as I was explaining to Emiliano, it looks like it stops when you look at the graph, but you cannot stop as you're approaching an asymptote. Does that make sense? So like if you were to zoom in and go to 2.999999, it would still have a value because it's trying to get closer and closer to 3. So your range is going to be from negative infinity to positive infinity. It's not stopping. The graph may give you the feeling that it stopped, but it doesn't stop. And your asymptote, that's at x equals 3. It's a vertical asymptote. Your intercept, your for sure intercept is that your x-intercept is at 2, 0. The one that you can see, the one that we're analyzing. Your y-intercept, so the y-intercept isn't exact. So your y-intercept is just saying if I plug in 0 for x, what do I have? So if I plug in 0 for x here, where is it at? So 3 minus 0 is 3, right? 3 minus 0 is going to be 3. And then it's going to be, the 2 is actually in the front. So your y-intercept, let me work it out here so I can say it again. When you're looking for your y-intercept, that's g of 0. Agreed? So g of 0 equals, I'm going to move my power to the front, 2 natural log of 3 minus 0. This gives me 2 natural log of 3. So 2 times the natural log of 3. That's what this value is. It's not quite at 2. It's at 2 natural log of 3. So your y-intercept is at 0, comma 2 natural log of 3. That's the exact value. Now you can type it in and find the approximate. You also could just go look at the graph, the table, and see the approximate. But that's where it's at. Okay, in this case, this function is function behavior. It's decreasing, agreed? It's continuous. And it's what? Concavity is cave down. Describing your limits. When we describe limits, we read our graphs from left to right. So the limit as x goes to negative infinity, what is f of x doing? And g of x, I'm sorry. It's not f of x, it is a g. What is g of x doing? As I'm going forever to the left, what is the function doing? Infinity. And the limit as you approach three, but from the left. If I'm coming from the left, what is g of x doing? It's heading towards negative infinity. Even though on the graph of the calculator, it looks like it stopped, it is continuing. Got it? And that concludes this part.